All right, so mean value theorem. So the mean value theorem is about average values of functions. So we have some function f of x. We want it to be continuous and differentiable. And an average value of a function is when you have 2 points. So we've got this interval a, b. And then we look at f of b minus f of a over b minus a. So this is the average value of the function over that interval. And what the mean value theorem says, as long as the function is continuous and differentiable, this average value here, there is some point c, so there's some x value c inside that interval ab. And actually it could be at the endpoints, anywhere in the interval ab, where f prime of c has that same average value. Now, you may recognize this average value here as the slope of the secant line between the 2 points. So this is also slope of secant to this function f of x through this interval. So we could say through the points a f of a and b f of b. And this is related to the intermediate value theorem, which we talked about a little while back. And this is important for pretty much most of the calculus we do from here on in, especially next quarter. This is going to come back in some important aspects of the next part of calculus when we reverse differentiation and look at the area problem. So we've got some function. So there's my f of x. And then we pick some interval, a to b. Again, we're assuming the function was a nice smooth curve, continuous, differentiable. And then there's tangent line through those 2 points, right? And that is also, the slope of that tangent line happens to be the average value of the function on that interval. Okay? So total change in y over total change in x, that gives us an average, also the slope. And what the intermediate value, or the mean value theorem, excuse me, says is that there's going to be some x value here, somewhere in between. Could be at the end point, could be right in the middle, it could be off to the left, where we have a tangent line that matches that secant line there. So they have the same slope. So the secant line has some slope, and we're guaranteed that there's a x value in there such that the tangent line has exactly the same slope. Right? So there's a bunch of applications to this. One of the applications I actually covered early last week because I think it's the most important application, and that's about increasing and decreasing functions. So important consequence of the mean value theorem, MVT for short, is that if a function is increasing on an interval, say at x equals c, then f prime of c is going to be greater than 0. And then if f of x is decreasing, oops, wrong color, there we go. then f prime of c is going to be less than 0, right? So decreasing, we get a negative slope. And we're connecting it to the derivative function. And if it's increasing, we get this positive slope. I actually did a proof of that in class last time we met. And essentially, it's related to the mean value theorem. There's a couple other applications of the mean value theorem, like Rolle's theorem, and they're kind of important, but not that important. And so we're just going to test out the mean value theorem in the homework in this section. So I'm just going to go over a couple of examples of how that works. And I think you'll find this isn't too bad. Question, am I not teaching Calculus 2? I am not. I was torn about it, but I have too many other classes to teach. I also teach math for elementary school teachers and statistics and quantitative literacy, and throwing Calculus 2 on top of that was more than I have time for. So Pete Hernberg, I believe, is going to be teaching Calculus 2, and he is awesome. He's super excited about teaching it, and I think you guys will really enjoy Pete. He is a great guy. But I'm sorry I don't get to work with you on that because Calculus 2 is wicked cool. We do like 3-dimensional stuff and areas, and we like pump water out of tanks and see how much work it is, and lots of fun stuff in there. All right, but we gotta have fun with this for now. So we'll come back to this consequence of the mean value theorem, but let's just exercise the mean value theorem in a couple of examples. So again, mean value theorem says this average value, which we're familiar with as the slope of a secant, so it turns out it has this other cool interpretation that's important to other areas of math and calculus. And as long as our function is continuous and differentiable, we're guaranteed inside the interval where we have that secant line, we have a tangent line with the same slope. And we could have more than one, it could be a bunch of them. So we'll find that out too here. All right, so first example, pretty straightforward one is, let's stop writing in red, it looks angry. F of x equals the square root of x. And we're gonna look at the interval from 0 to 4. And what we wanna do first with the mean value theorem, excuse me, get those confused because they're related. And again, we're not proving the mean value theorem. That's if you go on in math, like if you major in math, you'll learn to prove that in like a class that proves things in more detail about calculus called analysis, math analysis. So we're just going to say, hey, yeah, it works. So the mean value theorem says, all right, find f of 0. All right, that's 0. And then find f of 4. Okay, f of 4 is the square root of 4 or 2. And then it says find the slope there. Right, so I call it the slope of the secant line. It's also the average value of the function on that interval. So that average is just going to be 2 minus 0, right? Change in y over change in x, 4 minus 0. And so I get a slope of 1/2 through those 2 points there. So again, like if you look at a table of values, x, y, we're looking at the point 0, 0 and the point 4, 2. And we just found the slope in there to be 1/2. So next thing we want to do is say, okay, if that slope is 1/2, then the mean value theorem says, all right, once you have that slope, you can take the derivative, set it equal to that slope, and pray you can solve for x. And a lot of the times we can. So let's see, what's the derivative? So this is one I hope you have memorized off the top of your head. It's 1 over twice the square root of x. And we want to know when it's equal to 1/2. And so we can multiply both sides by 2. That cleans things up a bit. So then we get 1 over the square root of x is equal to 1. And then we could flip both sides. So the square root of x over 1, or just the square root of x, is equal to 1 over 1, which is just 1. And so squaring both sides, we get, hey, looks like x equals 1. And we can double check that. F prime of 1 is 1 over twice the square root of 1, which is 1/2. All right, so let's take a look at the graph of this. And I made a little Geogebra widget to kind of play with this one just for fun. So I'll share that in the chat and in the description of the video on YouTube. GeoGebra. Let's get the share link. You guys want to play with this. And when you first get into it, it's zoomed out. So just refresh. And one thing I like about GeoGebra is it's easier to scale than Desmos. But as we saw a few weeks ago, sometimes Desmos works better. Oh, I must have resaved it to the right scale. Okay, cool. So the way I set this up, I have this slider with this value called A. A then creates this point B. I've got this other point, capital A. Sorry, that's a little confusing, the little A's and the big A's. I should have chose my variables better. The big A is fixed here at the origin, but I can move point B around either by grabbing it and sliding it and say, hey, come over to 4 here. And GeoGebra has like a snap to grid feature. So if you get near a nice point, it will try to just magnetically jump to it. So you can see here, I'm at the point 4, 2 when I move that. Or I can grab the slider and move it around. Or I can set that X value A to whatever number I want. So I could just say, hey, be exactly 2, please, hit enter. Or I could say, hey, be exactly 4, please. Bang. And so then down here, I have it calculate the slope. What the heck was I doing there? Oh, I did it in general for, this is the slope of the secant line, assuming we have the point 0, 0 is what that is right there. And then I just use that down here to find that secant line. And then I told GeoGebra to just give me a tangent line at that point right there. So GeoGebra just automatically finds a parallel line for me where one of the points on that line happens to be on my function. So how I created this is a whole nother story. If you want to show how to make, if you want to see how to make cool things in GeoGebra, see me after class sometime and I can show you how I play with GeoGebra. It's fun. Anyway, what I can see here though is that just kind of the mean value theorem in action is that for any other point I pick, and I just happen to start at 0, 0 here, it's more complicated to have 2 points that slide. I have a tangent line, and that tangent line has a point inside the interval. Okay, so that's what the mean value theorem says. We can take any average interval value of the function and summarize it with a single point on the function, which is pretty powerful. All right, let's try another example. Back here, new page. This one right here is a little bit more work. So we're going to take a polynomial, f of x equals 2x cubed minus 15x squared minus 36x plus 1. And the interval is going to be from -4 to 8. So I'm going to whip out a calculator right away because I need to know what is f of -4. I need to know what is f of -8 because I want to be able to find the slope of the secant, that average value, which is f of 8, oops, -8, positive 8, minus f of -4 over 8 minus -4. Right, so we want to know what that slope is. So then we can apply the tangent to it. So let's just plug this into a calculator. Let's switch over to Desmos. F of x is 2x cubed minus 15x squared minus 36 plus 1. 36x, sorry. Okay, looks good. And then I can see it is swooping somehow through here, so I'm going to have to adjust my scale to get an idea about how to adjust the scale, aside from just zooming wildly with my wheel on my mouse or pinching on my tablet. I'm just going to say, well, what is f of -4, by the way? F of -4 is -223, so I need to go down quite a bit. And let's see where f of 8 is. F of 8 It's also negative 223. Interesting. All right, so I have a secant line through 2 points at the same vertical level, so the slope is going to be 0 there. So I'm going to write that down real quick because that's exciting. So we have a 0 slope here, right? We have this horizontal line. Horizontal secant line through this curve here. So we're looking for tangents that are horizontal. Okay, so basically we're just finding horizontal tangent lines. And we talked a little bit the other day about why horizontal tangent lines are cool on functions. So we'll get to that in a sec, but let's find them. So I need to adjust my scale for the y. I'm going to try going a little farther than that. Let's see what negative 300 looks like. Did I type something wrong? It's not happy. Do I get an extra negative? Ooh, okay. So there's negative 300. And I need to adjust. How do I get the scale here? Let's go like negative 10. I did it again. 10. Okay, a little better. And then we could go up a little higher. Maybe we'll try 100. It looks like we could go down lower still. So maybe we'll go negative 400. All right, that looks like a cute graph there. And then I think I want to see these two as points just for fun. So I could just modify them. Parentheses, negative 4 comma. Those parentheses. Do the same thing for this one. Parentheses 8 comma. All right, so there's those 2 points right there. And they are at the same vertical level. Whoa, back here. They both have the y value negative 223, negative 223. So I have a slope of 0 through them. And so I want to find the places on the curve where there's a slope of 0 also. And one thing we were learning before is that if the slope over here of the curve, this is increasing, the slope is positive. Over here, we're decreasing, the slope is negative. If we go from a positive slope to a negative slope, we have to hit a 0 slope in between, and that's at the top. So finding those 0 slopes is finding maxima and minima for the function. Okay, so we're tying all this together here with the stuff we've been working on. Oops, that button. There we go. All right, so next step, finding horizontal tangent lines, we need our slope function, f prime of x. So f prime of x is 6x squared minus 30x minus 36. And according to that up there, I want to set this equal to 0 and then solve for x. And so the homework problems are just like the last two I did. Here's an interval. Find the slope of the function of the tangent line, the secant line on that interval, and then take that slope and try to find through the tangent a couple of x values or one x value. So here, solving this, I would choose to divide by 6 on both sides. 0 divided by 6 is still 0. So I get x squared minus 5x minus 6 equals 0. And that looks like it factors as x minus 6 times x plus 1, negative 6, negative 5. Yep, that one works. And so if x, oops, ahead of myself, minus 6 equals 0, adding 6 over, x is 6, or x plus 1 equals 0, subtracting 1, x equals negative 1. And that, I think, looked good on my graph. So if I go and find the point negative 1, f of negative 1, that should be right on top there, bullseye. And then if I plot the point 6, comma f of 6, bang, right at the bottom there. And we're going to have horizontal tangents in each of those places. Done. Yeah, so the homework's pretty straightforward. Given a function, given an interval, find the slope of the secant line, which is also the average value of the function. Now, sometimes that average value is 0, and sometimes it's not, like here it was 1/2. So then we just set the derivative equal to it, hope we can solve for x, and we have our answers. So it's just, this homework is pretty straightforward. Again, it's just saying, hey, look, the mean value theorem works, right? It gives us this tangent line related to the average value of the function. And again, for me, the most powerful part of this section here is this consequence about increasing and decreasing functions. That if a function is increasing, it's got a positive slope. If it's decreasing, it's got a negative slope. And the derivative is the slope function. So we're connecting increasing and decreasing to the derivative. And we can take that a step further as we've been doing. All right, so we have the power of the first derivative here. So the first derivative tells us a few things about a function. So if, I'm going to state this in reverse, if f of c is greater than 0, right, positive slope, then f of x is increasing, right, uphill from right to left. If f of c, right, so some value we plug in for x, if we have, oops, sorry, this has to be the derivative, f prime, slope, then f of x, the function itself, is decreasing. Right, so heading downhill. And from the intermediate value theorem, if you go from positive to negative, so let's just graph the derivative here for fun. So d of x, its values equals 6x squared, yeah, minus 30x minus 36. What I should see is everywhere I have a horizontal tangent, right, that red point, the derivative should have a corresponding 0. And so here I have a horizontal tangent at the blue point, and this has a corresponding 0, the derivative function. So let's turn off the original function for a minute. And I see this derivative function is just some function on its own. It's positive over here, it's negative over here, and so in between it has to be 0 if the function was continuous. And remember, the mean value theorem and the intermediate value theorem say, hey, we got to have a continuous function on these intervals. Because if it jumps, then all kinds of stuff can happen. So no jumping around, no breaks in the function. So then another consequence we have of this first derivative here if prime of x is positive, can I spell today? Not enough coffee. Let's see. Something in the chat. What's up, Cole? The y-intercepts, the x-intercepts, you mean, are the same as the max and the min. Yes, that's what I was just pointing out there. So if we go back to that graph and turn this sucker back on, yeah, so if the derivative function has a 0, an x-intercept, then the original function should have a max or a min. The derivative has a 0. The original function has a max or a min. And just to make that clear, we can draw a vertical line, x equals -1, 6. Yeah, so there is that connection. And so that's what the mean value theorem, these are some important consequences up to it related to the derivative. Nice. And that's our focus at the moment. So if f of x is positive on one side of x equals c and negative on the other, then f prime of c is 0, and f of c is an extreme value. And we'll classify these as max and mins in a second. But this is kind of a general idea. This is related to what we were talking about the other day, critical values, critical points. And critical values happen any place that f prime of c is equal to 0, or any place f prime of c does not exist. And these critical values, the other day I was calling them candidates. Candidates for extreme values, for extreme points. So they give us a starting point. So if we can find the places the derivative is 0 or undefined, then we have potential extreme values. Then we have to go further and say, okay, did the derivative actually change sign? And then if it changed sign, we can say, oh, okay. So taking it just a little bit farther, maxes and mins, right? Maximum values of functions. So if in this case f prime of x is greater than 0, f prime, there we go. For x less than c, so we've got some x value and then we pick another x value over here, let's say, and we find that there's a positive slope through there. So this is just some other x value there. F prime of x there is positive. We have a positive slope going in, so we're on the left side of C. And f prime of x is less than 0 for x greater than c, then f of c is a max. Now, we don't know if it's local or absolute. That's a whole nother test we have to make, but we know we have a maximum there. So we have some x value on the other side here, any x value we picked, and we're reasonably close to c, and we find that f prime of x is less than 0 on that side. Is again, the assumption here is the function is continuous, then we must have a maximum at the top here. And the y value, right, f of c, that's the max, not c. C is just what gets us there. and then corresponding definition for a minimum of a function. So we're connecting these max and mins to our derivative function. And when we put all this together like this is what's called the first derivative test for a function. So let's state minimum, and then let's do it with a couple of examples. So in this case, we have our derivative less than 0, right? So we have a negative slope. Function is decreasing, is what that tells us. For x less than c, and f prime of x is greater than 0, so we have this positive slope. In other words, the function's increasing for x greater than c, and f of c is a minimum. Again, similar idea, x equals c, we got some point. And for x values to the left, for any one I pick here, what I see is that the function has a negative slope. So again, f prime of x is less than 0. And on the other side, I pick some x values, and I see that f prime of x is greater than 0. So we're going uphill there. And in between, it must have a minimum value. So this would be the minimum. So f of c is a minimum. So let's test that out for the function we were just playing with that we could see the graph of. So we'll just look at this function right here again, and we already have a bit of information about it. We know that the derivative is 0 at -1 or 6. So let's re-summarize that. So f of x equals 2x cubed minus 15x squared minus 36x plus 1. You got that right? Yep. F prime of x, the derivative, slope function, 6x squared minus 30x minus 36. And earlier we took our f prime of x and we set it equal to 0, and we found that x was equal to -1 or 6. So the next step, and I did an example like this the other day, is I make a number line and I take a look at those values. So I only care about on the number line, x equals -1, and somewhere over here, x equals 6. And so I think something's happening here. These numbers right here, -1 and 6, are called critical values. And critical values are candidates for extreme points. And so the way the first derivative test goes, first derivative test, and this is what I was saying, this is like one of the big powerful ideas about the first derivative. Test is to do some sign checks to see what's going on. So we just pick some convenient numbers in this interval here. So 0 is a nice convenient number. I would pick x equals 0 in between here. And then on the other side, doesn't really matter. I could pick any number I want. So maybe I'll just pick 7. You could pick 10 if you wanted, 6.1. And then over here, I guess I'm just going to pick -2. So I pick some x values to test. And I want to know is what's the sign of f prime of x? So what's the sign of f prime of -2? What's the sign of f prime of 0? What's the sign of f prime of 7? Okay. And if we find there's a change in sign, then we know we went from increasing to decreasing or decreasing to increasing. We can classify what's going on at the actual critical value. So calculator time. Let's see. This picture got a little bit too busy. Well, I want to know what's the derivative at -2. That's 48. So that means we have a positive slope. Function is increasing. And then I want to know what's going on at 0, -36. That one's pretty obvious. Negative slope there, decreasing. And so if I go from increasing to decreasing, then in the middle here, I must have a maximum of whatever f of -1 is. And we have to calculate that too. So we also want to check out 7. So any number on the other side of 6, so it doesn't matter whether I plug in 7, 8, or 9, or 10, I'm getting a positive number. 7 had a slope of 48. So we have a positive slope. That means the function is increasing in that region, right? What region am I talking about? I'm talking about any number for any x value greater than 6, we're increasing. So it went from decreasing to increasing, so in the middle here, we must have a minimum. And the minimum is whatever f of 6 is. So let's find those next. What's our max and our min values? And I think I plotted those points. F of 1 is 20. And f of 6 is -323. So y equals 20 is a max, and then -323, that's again a y value, that's our minimum. Happened at 6. Now, the other thing to find out is it a local or absolute? Now we can see from the graph that these are local maxes and mins, and the real test for that is for on this interval over here, we would want to say, okay, what is the limit to double check that that's a local? And we'll look at that in the next section as x goes to infinity of f of x. And we'd also want to test this side, what's going on over here. We'd want to know what's the limit as x goes to -infinity, heads to the left forever of f of x. What are those guys doing, right? The end behavior of the function. And you talked about that a bit when you were taking your first pre-calculus class, probably. So the first derivative test just says, hey, find the places where the derivative is 0 or undefined. Once you have those, break up a number line. Right, so that's what we did here. We said, okay, here are critical values. Split up the number line and then make some tests for values in between and see what's going on there. So one more idea I'm going to introduce, and we'll do another example. And I want to modify this. Let's get rid of some stuff. I'm going to throw a slider in here. Let's call it C equals, and we'll start with 2 maybe. And my derivative back. Oops, shouldn't have deleted that one. What I'm going to do is I'm going to set up a tangent line because I want to show you something interesting. So D is 6x squared x minus 36. And then I want to use that to find the slope of a tangent line. So a couple of things I need here. I want the point, C, f of C. And I want to know the slope at that point. So let's call that m equals the derivative at C. Okay, so the slope is -72. We can see, yeah, it's definitely negative in this region right there. And then I want the tangent line. Y minus y1 f of c equals the slope m times x minus c. Oops, that's not a c. That's a c. Okay, so there's my tangent line. And And the reason I set it up like this is this slider now lets me move that tangent line around on that point. So I don't really need to see the derivative function. I just want to see the tangent line. So let's clean it up a little bit. And if you guys want to play with this too, I will share it in the chat. Okay. And again, when that happens, you get your own copy of this sucker. I should get the name. Tangents. Enough. So I can either move the slider or I can grab that point and move it around. All right, so we know that up here at x equals -1, and I can force c to be -1 if I want. I have a horizontal tangent line, right? So I have the slope of 0 when c is -1. Now on the left side here, I have a positive slope. On the right side, I have a negative slope. And we know if we have values that go from positive to negative, they have to hit 0 in between. But there's another cool thing going on here. So check out the slope over here. So I'm somewhere, near -3-ish, and the slope is around 100 when c is near -3. So it's around 100 and something there. And then as I move that x value from -3 toward -2 and -1, watch what happens with the slope. What's happening with the slope as I move the x value from -3 toward -2? Right? It's dropping, right? So I'm over here at -3, slope's around 100. I move over toward -2, the slope drops to 63. I get closer to -1 here, the slope's dropping to 40-ish, 37. And the slope's gonna go from, over here around 100 all the way to 0. So just a note, on this part of the curve, as x goes from left to right, my slopes are decreasing. My slopes are decreasing, and they continue to decrease for a while. Okay, so -100-ish, or sorry, slope of 100, and then I have a slope of like 50, and then all of a sudden I have a slope of 0, and then I have a slope of -10-ish, -20-ish, -30. My slopes are still decreasing, right? -50, -60, -70-ish. And then all of a sudden, the slopes start going to go the other way. So over here, my slope is like -73-ish, but as I go this way more, all of a sudden it's -72, -70, -60. My slopes are now starting to increase. Okay, so something weird happens right in here. If I were to only focus, like if I were to just zoom in on this part of the curve right here, that looks kind of like a parabola, right? We would say that parabola is concave down. If we were to only look at this part of the curve here, hey, that kind of looks like a parabola. It's a concave up parabola. An interesting thing is, if you have a concave down object and you let x move from left to right, you should always see that the slopes, as the x values move, those tangent lines, these slopes are decreasing. So I go from 100 to 0, 0 to -70-ish. And as long as I stay on that concave down part of the curve, as x goes from left to right, my slopes are decreasing. So what I'm looking at is the rate of change of the slope. Interesting, what's that mean? So observation, and then we'll put this into some math. Oh, it's a funky O. Observation. Graph is concave down on an interval. Concave down interval. As x moves left to right, the slopes are decreasing. And so what I'm describing here is a rate of change of the slope. Rate of change of slope. Okay, so rate of change, that is a common phrase for derivative. Slope we get from a derivative. Derivative. And ooh, there we go. So what's going on here is I'm thinking about the derivative of the derivative. That is the second derivative. Okay, so check this out though. My slope is a function, right? My slope comes from f prime of x, and f prime of x is just some function. I was calling it d of x earlier. And this function d of x is decreasing, is what I observed. If it's decreasing, so if d, some function, is decreasing, we learned earlier that that means its derivative must be negative. Negative derivative. D, I'm looking at d's derivative. D is f prime of x, so d's derivative, d prime of x, is really the second derivative of f of x. So let's check this out. Let's look at the second derivative of our function to see what's going on. So our derivative function, let's see, am I running out of room there? Yeah, totally out of room there. This is not the last example we have time for. So again, we started with f of x equals 2x cubed minus 15x squared minus 36x plus 1. We found the derivative function, f prime of x, the slope function, was 6x squared minus 30x minus 36. We also found that it had these critical points, critical values, at -1 and 6. Now we're looking at the second derivative, the rate of change of the slope. That would be 12x minus 30. And what I want to know, a couple of things about this, is if I check out what is, let's stick with red, what is f double prime, the second derivative at -1, that critical value? If I plug it in here, that gives me 12 times -1 minus 30, which is -42. So I have a negative second derivative. That negative second derivative implies that f of x is concave down there. So if f of x is concave down and my slope changes sign there, which is kind of what the critical value tells me, so I have a concave down when x is -1, then shouldn't that be a max? Right? And then correspondingly, I guess I need to stick with red for a minute. If we say, hey, what's going on with the second derivative at 6? I get 12 times 6 minus 30. Ooh, 12 times 6 is what? 72 minus 30. That's going to give me 42, positive 42. Kind of a coincidence that they are symmetric, negative, positive numbers. But that right there implies that positive number for the second derivative, that f of x is concave up. And something else is going on at 6, right? We believed that there was a change in sign of the derivative. Now, just because we have a critical value doesn't mean we definitely have a change in sign of the slope, but we have now extra evidence because of the concave up at x equals 6. And so that is probably a minimum. And throwing the second derivative in here is what we call the second derivative test, and it gives us further evidence about what's going on with the function. Now we could clearly see the graph of this function, but some functions are more complicated. So we're using these simpler functions to get an idea about what more complicated functions are doing. You might remember I tried to graph a special sine function in Geogebra the other day, and Geogebra crashed on me couldn't compute. Interesting thing is what happens in the middle here. I have a negative second derivative at negative x equals -1. I have a positive at 6. So somewhere between x equals -1 and x equals 6, we should hit 0. So I want to know when is f double prime of x equal to 0. So 12x minus 30 equals 0. Add 30, divide by 12. Let's see, 30 over 12 cleans up a little bit to what? 15 over, let's see, half of 30 is 15 over 6. Do it again. Oh, I guess 6 went into both of those. 5 halves. Thank you, Kelsey. I'm a little slow this morning, apparently. 5 halves, which is 2.5. So what we should see is a change in concavity at x equals 2.5. Let's go back and look. X equals 2. I don't know about you guys, but I think this is wicked exciting. All right. So let's pull the tangent line over there. Yeah, so where our belief now is on that, based on that calculation, here's x equals 2.5, that vertical blue line. To the left, this graph is concave down, and to the right, it is concave up. Kind of cool. That point of change of concavity is called an inflection point. So the point 2.5, whatever f of 2.5 is, we didn't actually calculate that. That's called an inflection point. And for me as a bike rider, an inflection point is a cool thing because that's when the hill starts to get less steep. And we'll talk more about that tomorrow. So we're out of time for fun with calculus. Thank you for playing. We are still a day behind. For now, what I'm going to do is the homework. I would like you to try and finish the mean value homework today. If you don't get it done today, then use a late pass. Let me know, and I'll redeem your late pass for you. And then we're going to continue working on shapes of graph tomorrow, and I will probably shift that due date. Bye-bye. Adios.